Hello, everyone, and welcome to today's Design Expert New User webinar. The goal really of this session is to help new users become familiar with design of experiment concepts and also to introduce Design Expert software for the creation and analysis of several types of experiments. By way of personal introduction, my name is Richard Williams, and I've been a studies consultant for roughly 6 or 7 years now. But prior to that, I spent 38 years in the chemical industry, focused on roles for product and process development and improvement. By training, I'm a chemical engineer with a bachelor's degree and also a Six Sigma Master Black Belt. In my experience, I feel that DOE has been underutilized for problem solving and process optimization. But equally, I think DOE should be the tool of choice to help us launch reliable products and processes from the very start. This really is the idea behind quality by design, or design for Six Sigma. Over the past 10 years or so, I focused on providing training for product and process improvement tools. So today I'm really happy to present this webinar to get you started with design of experiments. I must say that this is actually a very broad topic, and in 1 hour we will only be able to scratch the surface. But that said, we're actually going to go through three example problems in this brief 1 hour webinar, and you're going to be exposed to a lot of the features in the software, and hopefully come away with a reasonable understanding of how DOE could be of help to you. Okay, so let's dig in. So to prevent audio disruptions, all attendees will be on mute. Okay, so during the webinar, though, if you have questions in the GoToWebinar list, there's a bar or a tab for questions. I'll be taking a look at that as often as I can, and some of the more brief questions I will address as we continue. If there's anything a little bit more complicated or something I can't get to, please follow up by sending those questions to stathelp@staties.com, and we'll be happy to give you a little bit more explanation for your inquiry. There will be a recording and the slides available for this webinar, and they will be posted on the webinars page of our of the Staties website within a few business days. So really the primary goals for today is, first and foremost, why would we as experimenters want to think about using design of experiments as a methodology as opposed to any other approach that we may have used? Well, we're also going to introduce the Design-Expert software with hands-on or a true demonstration. We're actually going to see it in action. Want to make you aware of some of the different types of applications and experimental design types that exist. And then we'll give you a little bit more in terms of next steps. Where do you go from here after a 1 hour webinar? How can you get more information, get more training, and continue the journey a little bit? So let me pause here for a moment and ask you to try to find in the tool set the little raise your hand button. Let me know if you're hearing this and that you're with me. There we go. Okay, I got a couple. That's always a good thing. It's always a good experience to find that people can hear what I'm saying before I get too far into it. So thank you for that. Okay, so Staties has two different versions of DOE software. There's the Design-Expert, it says version 13. I think currently we're using an annual, it's called Design-Expert Annual. But in any event, Design-Expert is the product that's been with us since the beginning, since the mid-1980s. Obviously, the features have advanced considerably over that period of time. But there is a new flagship product called Staties 360, which really bolts on some additional tools, really more advanced features that certain clients have asked for that go beyond the basics of Design-Expert version 13. So just to make you aware that there is a couple of different products out there. Honestly, for most people who are new to DOE, everything you need will be in the Design-Expert annual or the 13 product. Okay, let's see. So kind of the agenda, what we're going to do is we're going to briefly talk about design of experiments and, what's in it for me? Why would I do this? Okay, so once we get past that, then we're going to do three DOEs together. So I usually manage to get through this webinar in 59 minutes and 59 seconds. So let's see if I can stay on pace. There's a lot here. But we'll do a factorial demo where we try to understand the impact of different factors on a process. Also the interactions, and we'll talk more about interactions in a moment. We're going to look at a response surface design where the goal of the experiment will be to really find the optimal conditions. Then we're going to look at the specialized tools that we have for a mixture design where we can find the sweet spot of a formulation. We have optimal custom designs for every challenge where you could just basically let the software build a custom DOE for you, and we'll take a brief look at what that's about as well. All right, so what's in it for me? Well, first of all, what is a designed experiment? Well, a lot of us tend to think of the world as a process, and I know we deal with formulations and mixtures, but I think the concepts are best explained here. We have controllable factors. Let's imagine that we're making cookies in our household kitchen. We have some, and we want to optimize the flavor of the cookie. Well, we have some controllable factors. I mean, sure, we could play with the formulation, but we're dealing with the process here a little bit. So what kind of controllable factors might we imagine? Well, maybe time in the oven, temperature of the oven, maybe the type of cookie sheet that we use. Maybe the type of grease we might apply to the cookie sheet, maybe the oven rack, maybe there's a difference with the lower rack to the upper rack. So there's some controllable factors, things that you and I could actually change. And then what we're going to do is we're going to measure some response, meaning the Y variable, if you will, right? We're going to have the flavor of the cookie as measured by the average of 5 taste testers, however we define that. So our goal is to establish a connection between the controllable X factors and the one or more responses of interest. In this case, we'll just look at taste, or maybe we have two. Maybe we can add the yield. What percentage of the cookies turn out good? Okay, they're not burned or undercooked. And then the problem we run into is we also have these noise factors. For example, if we're going to use the average of 5 taste testers, well, maybe these people won't rate the same cookie identically each time. The measurement system might be a little bit noisy. Or perhaps, when we set the oven temperature for 350 Fahrenheit, well, what we set is the dial. We set it to 350, but what's going on inside the oven may wander around. Maybe sometimes it's 325, maybe sometimes it's 375, and that's going to have an impact on the cookie. Maybe there's hot spots and cold spots inside the oven, and these are all things that are going to introduce some noise or some variation in our responses. So our goal as experimenters is to have a defendable connection between the X's and Y's despite the noise created by the noise factors, the Z factors. So a designed experiment is going to be a planned approach to determine these cause and effect relationships. It's not just going to collect a haphazard random set of data that we're going to try to analyze using some statistical tools, but we're actually going to prescribe the runs that should be run in order to take advantage of some mathematical properties so that we can analyze and defend the correlations that we see between the X's and the Y's, and also this thing called interactions that we'll talk about in the next slide. But with a DOE, we're actually going to change more than one thing at a time, okay? We're often taught that one factor at a time experimentation is the only way we can understand a system, that we have to hold everything constant and only change one thing at a time, right? We hold the time in the oven constant and we study the temperature, okay? Or we hold everything else constant and we study the rack in the oven, okay? Well, the problem with one factor at a time experimentation is you can't identify interactions. So really a design of experiment will benefit from multi-factor testing. We will intentionally change more than one thing at the same time in a very prescribed manner so that we can mathematically untangle the mysteries of the situation. So let's look at this little plot in the upper right. So let's say we're baking cookies in the oven again, and we are looking at the yield of the cookies, right? We don't want to burn them. We don't want to undercook them. We want them just right. And we're looking at the temperature in the oven, right? That goes from low to high, whatever we decide those settings are. Maybe it's 325 to 375. I don't know, whatever they're going to be, low and high. And then we have a cook time. We have short and we have long. Well, let's look at the dotted line. So with a short cook time and a low temperature, we have a low yield. That's because we are undercooking some of the cookies. As we increase the temperature, we're getting more and more of them properly cooked. So we actually improve the yield. If we have a long cook time and a low temperature, well, we have good yield, but as we increase the temperature, we end up burning more of the cookies, so our yield falls off. So an interaction, the way I define an interaction is simply this. An interaction is when the impact of one factor depends on the set point of another factor, right? So in this case, the impact of the cook time depends on the temperature, or you can say it in reverse. The impact of temperature depends on the cook time. Okay, there's a connection between the two. One factor at a time experimentation cannot identify these interactions. Interactions frequently play a very important role for process improvement. And so the idea here is we need to set up our experiments in order to find interactions. DOE with multi-factor experimentation by its parallel processing provides more information in fewer runs than one factor at a time experiments. We're going to do less work and get more information. That's the goal. And on top of that, we're going to apply some statistics to the whole story so that now we just have, a clear indication that the things that we say matter do in fact matter. We have statistical evidence that we can take to the bank. So we have a lot of different experimental types. We're going to do a factorial. We're also going to come into response surface, and we're going to do a form of mixture that is actually going to come all the way down to the custom design. So we've got quite a bit we're going to do. A lot of the menu choices we're going to see today. We have a full array of designs and tools to address three overarching goals. First of all, we can screen. What does that mean? Well, let's imagine that we brainstormed all the different things that it could impact the flavor of a cookie, right? We listed everything we just hinted at, the rack in the oven, the time, temperature, etc. Maybe you could sprinkle sugar on top of the cookie or not. So it's a categorical choice of yes, no. Maybe we imagine that the temperature in the ambient temperature in the room or the ambient humidity in the room might have an impact on it. So there's all kinds of different things that we could imagine. And a screening experiment will be to identify the critical few, which ones really drive the process. And so we want to do screening designs to narrow down the list, and we want to do that with as few runs as possible. So that's what a screening design is. And once we know the important factors, then we can characterize them more completely. We can look at the main effects, but also characterize these interactions of interest. And we can also do a response surface type design where we can optimize. So let's get into this a little bit more. Well, okay. So I don't want to dig too deeply into this, but there is a little bit of a script or method that we follow when we set up a DOE. I mean, first of all, and it's true for any experiment, I suppose, is that we want to define the objective, but in terms of a measurable response. We want to be very clear about that. We want to improve the taste score of a cookie from 5 to 7, for example, okay, as measured by the average of 5 taste testers. Then we're going to look at the input factors to study, right? It might be all the things we just listed to improve the taste of a cookie. Then we're going to select our design. How are we going to do the experiment itself? And we're going to give you some choices in our software to help you do that. Point 4, you get to do the hard part. You have to actually conduct the experiment. We're going to step back in with 5, 6, 7, and even 8 to actually guide you in the software to analyze your results, look for any abnormalities in the data, help you resolve those. We're going to use graphs when we can, but we have other methods for interpreting the outcomes that we see. And then we're going to optimize. We can optimize using some tools that you're going to see momentarily. Okay, so that's basically the script. So let's do a factorial demo. So a factorial design is one in which we're going to look at the impact of various factors on a process. And then we're going to also characterize the vital interactions. And mainly when we say that, we're primarily interested in 2-factor interactions, where one factor depends on the set point of another. But you can, on occasion, have higher order interaction terms, where maybe a 3-factor interaction, where the impact of one factor not only depends on a second factor, but also a third. Okay, so that's uncommon. 2-factor interactions are the most common. All right, so here's the first system. Pardon me, I'm a chemical engineer, so I always like these chemical examples, but here we go. We want to find the conditions that maximize the yield of a chemical reaction. Okay, we have 5 factors that we're going to look at, right, listed there. The last one is an interesting one. It's a categoric choice. We are either going to put nitrogen in the headspace of this reactor, or we're going to allow it to have just air in there, right? So it'll be faster and less costly if we can use air, but we suspect that might impact the yield of the chemical reaction. Okay, so those are the 5 factors. Now, the one thing that we want to do, and I'm going to go quickly through this, but I hope you can get the idea of it. Honestly, this is probably conceptually the most difficult thing we're going to talk about. But here's the underlying principle. The more data that we collect, right, the more runs that we do, the more certain we will become of our story. The more certain we will be that we have found the factors of significance and can make adequate predictions from our data. Right? We all know that intuitively. A lot of data is going to be more helpful than less data. Now the problem is we want to make sure that we conduct this experiment in such a way that we can reveal what we feel we need to discover with as little work as possible. So we ask ourselves 2 questions. We want to look at the signal, in other words, understand what we're trying to find, and how noisy is the system. And this is oftentimes the most difficult thing to estimate, but really all we're looking for is estimates on these 2 properties, and they will drive something called a power calculation. We want to make sure that the experiment contains enough runs that we have adequate power, adequate ability to find what we're looking for. So the signal is what we're looking for. Any improvement less than the amount that we say will be deemed unimportant. So if I'm trying to improve the yield of this reaction system, and let's say I'm currently running at 80%, well, maybe if I change it to 80.1%, that's not important. That's too small of a value. You know, maybe I need 2 or 3 percentage points in order to be regarded as important. And in this case, that's what we're saying. We're saying that we're looking for the factors that will contribute at least a change of 3 percentage points when it goes from its low level to its high level. It's a guess. So that's what we're saying we need to find. And then we're looking for the standard deviation. So the theory here, the idea here is, let's imagine we did the same exact conditions 10 times, and we got a little bit different results each time, and we calculated a standard deviation. Well, we're saying in this case that standard deviation would be something like 2%. Okay. Now, that's usually not how we get that standard deviation. We usually steal it from maybe a prior DOE or some manufacturing data or what have you. But at the end of the day, what we're trying to do is make an assessment for what we're looking for, the 3%, and how much noise we think is in the system. And that's going to drive a power calculation. And we'll see that in a moment. So let's go ahead and set this one up. So I have these 5 factors, and I want to create a design. So in the software, I'm going to use 360, the flagship product, but it's the same in Design-Expert. I will come over here. I got to switch tools here. I'm going to create new design, and that calls up this particular regular 2-level factorial design. This is kind of the splash page, or the most commonly run DOE, although arguably maybe it shouldn't be, but this is probably more DOEs have been run in this space than any other tool that we have. Along the left edge here, you see that there are several different design choices. We have the regular 2-level, we have minimum run characterized, we have these responsive surface designs that we're going to see a little later, we have mixture designs. So there are several different types of designs. Many people that have a casual awareness of DOE are probably aware of this particular design, the regular 2-level factorial design. So that's where we're going to begin. Along the top edge, we have the number of factors. Well, in this case, it's 5. And this diagonal group of white runs, white design choices, are the full factorial. A full factorial is when every factor will be tested against all the other factors at its low and high level. Okay, so we're going to test everything against each other at the high and low level. So we're going to click this one, the 32 run design. But notice there's a green one right above it that would cut the work in half. So we'll comment about that a little later. For now, we're going to do the full factorial. So I click next, and that calls up the entry sheet where we begin to enter our information. So here, the first factor, what did we say? It was going to be feed rate. And it was liters per, what was it, minute, and it's a numeric factor, and it's going to go from 10 to 15, and then we can start loading all the other ones. Now, in the interest of time, what I'm going to do here is go ahead. Well, that didn't work. Let's see. There we go. So I have one pre-filled out here. Actually, I want to come back up to here. There we go. So here's all the information that we have in there, right? It's a regular 2-level factorial. So we manually enter together the feed rate, and now I have the rest of them populated. The atmosphere is a categoric factor, and that one is going to be in nitrogen or air, right? So we have 2 different choices for that. All right, it's a categoric. It's either this or it's that. So then we hit next. And here's where we're going to do that power calculation. We said that we want to see the factors that cause a 3 percentage point change. And we said the standard deviation was 2. So the ratio is 3 to 2, or 1.5. That's what drives the power calculation. And when I hit next, I see that the power, my ability to find, if factor A causes a 3 percentage point change, I have a 98% chance of discovering that. The blue boxes, when you see the blue boxes, the annotation boxes, those are going to tell us what we need to be paying attention to on any given panel, any given slide. So here, the power, we want to see that to be at least 80% or greater. You know, you can go higher than that, but we want a minimum threshold typically of 80%. Well, we're good here. We have 98. So we'll finish the design, and there it is. So these are the 32 runs that we would go conduct for ourselves. Okay, so we had to head off to the manufacturing environment and run all these different conditions. And then we're going to get data. Well, I have a way to quickly do that today. So let me jump back here. This one is reactor. There, now I have all my data. Okay. Well, once we have data, we're going to analyze it. So we come down from top to bottom here, underneath analysis, we click on yield and we start the analysis. And now in a full course, we'd explain this a bit more completely, but for now, let's just understand the half normal plot and what's going on here. The red line is there to represent where we believe the noise is in the system. Okay, so what these points are, let's just right click on one. That's the atmosphere factor. Okay, this one over here would be the CD interaction term, right? So the blue one over here is a 3-factor interaction term. So what it's saying is anything that's more or less along this red line is indistinguishable from noise in the system. And the things that pop off that red line are statistically significant, right? So it's a very easy graphical approach. These are the things that are going to be statistically significant. And then there's another test on the Pareto chart with statistical limits. But what we see is we have factor B, the catalyst. We have two factor interactions that are quite significant, right? They're way off the red line. 1 factor at a time experimentation would not let you discover the presence of these rather influential, high impact interaction terms. We also see factor D, the temperature involved, and also the atmosphere, whether it's nitrogen or air. All right, so then we also take a look at the ANOVA, the analysis of variance table. To make a long story short, what we're looking at here is the p-values that are very, very small, less than 0.05. Yes, they're all less than 0.05. So the items that we have selected on the graph are all statistically significant. And the overall model is statistically significant, right? It's that easy, right? So we're just going to tell you it is a significant model. The blue boxes, once again, are going to tell us the things that we're looking for here. Our fit statistics are good. It passes everything, all the requirements in the blue boxes. So we're good. Then we want to look at our diagnostic plots. And there's obviously a lot more here that we could talk about than we're going to have time for today. But basically, if you look at your residuals, the residuals are the predicted versus the actuals, right? So we use the model we created in the ANOVA to make predictions for each of the data points, and we look at the predicted value versus the actual value, and those residuals should have certain properties. They should be normally distributed. Well, this graph highlights that. We should have residual versus predicted with some properties that are okay. Inside the red lines, no big megaphone. So there's a bunch of different things that we're looking for on these diagnostic plots that we won't have time to cover in detail today, but these all look solid. They look good. So then we're going to come to the model graphics. Okay, well here it's going to highlight a 2-factor interaction plot because it detected we had interactions in our system. So what are we looking at here? We have catalyst along the bottom. We have 2 lines. We have the 2 temperatures that we evaluated, 140 and 180. Well, looks like we want the 180 versus the 140. But look at this, was all run at the nitrogen environment. I could also take a look at what happens in air. Okay, everything gets a little bit worse. So we know that we want to run this in nitrogen to have our best yield, right? The highest score on the left. Notice that there are 2 factors that don't have any influence. The agitation rate didn't matter. I can move that slider all over. And the agitation, right? So we've discovered some things that really don't have any bearing on the yield of the system, but we know three things that do, and that there's an interactive behavior amongst them, okay? So we know we want nitrogen, and if I click on this highest point here, it's going to do what's called a pairwise comparison. So that becomes the reference point, and all these other conditions are inferior. We know that because these whiskers don't cross the red line, don't cross the reference. And we also have an estimate of the yield that we would expect under those conditions at 93.64%. Okay, so really we've answered the question. We found the ideal conditions, and we've made an estimate for what the yield would end up being. Okay, so that's the first example. Let's drop back to the slides for a moment. So things to remember: a full factorial tests all possible combinations that characterize all main effects and all the interactions that are possible, right? In this case, we had 5 factors that we could have estimated with a full factorial all the way up to the 5-factor interaction term, but that is highly unlikely to exist. So we might be able to shortcut this a little bit, do a little bit less work. But if we do less work, we're going to have less power. You know, the more runs, the more power. And the power assesses the probability that an experiment will identify the important effects, and it's driven by that signal to noise ratio. In this case, I think we had 98%, so we had plenty of power. We want to be past the 80% threshold. Sometimes we'll be a little liberal with that. You know, you get up to 95%, you're pretty confident you're doing enough work, doing enough runs to reach valid conclusions. I mentioned that there were these green runs, so there was a green run with half as much work. So that would be one that we would have wanted to consider in this particular case had we done this. Why do 32 runs when you could get the job done with 16? Now, if we check the power at 16 runs, I think in this case we would have ended up with 17. Excuse me, 77% power. Well, that's probably close enough to 80 that I would be highly tempted to go run it. I do want to get to 80 usually, but you know, if I could cut the work in half, that might be sufficient to find what I'm looking for. Okay, so I might take a risk and go ahead and do that. The green ones will at least let you identify all the main effects and the 2-factor interactions, which are definitely the most common. You know, 3-factor interactions are quite unusual, very rare. Well, we definitely want to set up our experiments to be able to find at least 2-factor interactions. All right, so then we're going to get into a response surface demonstration where we can optimize a system. So with 2-factor interactions, all we're able to do in this response surface curve, right? So I have 2 factors here, x1 and x2, and all I'm looking at is what's taking place here. Well, the interaction term is allowing me to put a twist into that plane, but it can't elevate the center of the design space to chase a hill or a valley. Okay, so the very center of the design space is unaffected by the twisting plane. Okay, so that point, let me get the tool here. So that that point right in the center is unaffected by right. That's at the 0, 0, right? In 0, if both A and B are 0, then all you're getting is the overall average of your corner points. So at the very center, a twist in the plane or the 2-factor interaction term really isn't creating a hill or a valley. To get a hill or a valley, you need to bring in some quadratic terms, some squared. So here we're going to add the a squared and the b squared to actually create a curved surface, you know, and we do this when we suspect that the optimal conditions might reside someplace within the design space, that the factorial model and the interaction model might not be adequate to find the optimal conditions. All right, so here's the next case study. We're going to study three factors, and we have two properties that we're going to look at this time. We want conversion or yield again, and then we have another property for this little chemical case where we have a property called activity that we want it to be ideally 63, but it must be between 60 and 66, okay? And we're going to create something called a central composite design. And it kind of looks like this with three factors. So the blue would be the factorial points like we just ran in the previous example. Well, that was 5 factors. This is what it would look like for 3. But now we're going to bring in some center points, so points right in the interior center of the design space, the cube. And then we're also going to bring in these axial points, ideally points outside the design space that are going to help us better estimate those quadratic, that a squared, b squared, c squared terms. Okay, so that's called a central composite design, and that's what we're going to use for this particular case. So again, right, we're going to maximize the conversion, the yield, and try to achieve the targeted value for activity. So let's open that one up. Let's see here. We have, get the right one here. Is it this one? Not that one, not that one, not this one. Let's see, time, temperature, there we go. So in the menu of choice, right, we're gonna come down underneath the factorial designs. We're gonna go right past that, and we're now in the world of response surface designs. Response surface, where the goal is to optimize within the design space, within the cube. We have choices here, central composite, box, optimal, different choices here. And in the full course, we would explain in greater detail what all of those are for. But in this case, we're going to take the most commonly used one, the central composite. We have 3 numeric factors, time, temperature, catalyst, and these are the values. And we're going to take the standard default conditions and go ahead and set this up. So we'll hit next. Here's my 2 responses of interest. And we'll finish the design. Now notice that it didn't drive us to do a power calculation. Response surface designs are sized differently. They're not sized using power, right? The number of runs that are chosen and the way we look at it, we're going to size them for precision, which is a little bit beyond the scope of what we're going to talk about today. But as a general rule of thumb, response surface designs will be large enough that you don't need to be terribly concerned about sizing them. Although, never say never. Well, here it is. So let's get our data. And we'll load an existing simulation. This one's going to be called reaction. And there it is. So I have these different run conditions and the conversion and the activity achieved. Well, now we need to analyze both of the responses one at a time. So I will click on conversion. I'll start the analysis, and now I don't have my half normal plot where I just select the boxes. It's because we're doing a different style of DOE, and the way they analyze is now different. We're looking for the proper polynomial, the proper choice of terms that will properly fit to the data set. And it's recommending a quadratic. Okay, so make a long story short, we'll accept the recommendations. We'll click on the model. Here are the terms that it's going to include. We look at the ANOVA. We've seen that before. So here it is. I have a significant model. That's good. I want a not significant lack of fit. That's kind of inverted statistical doublespeak, but that's the ideal condition. We want our data to fit, and therefore we don't want significant lack of fit. These are all good. The blue boxes are telling me everything I need to know, and I'm happy with the analysis. We can look at the diagnostics, and there's really nothing really to be concerned about here. Maybe this point right here is a little bit odd, and I can look at where it falls on the other graphs, and yes, it's a little bit out of a line down here, I suppose. I can look at when I have a point that I might be concerned about. I can look at the bottom right charts to find out, well, how much do I care, right? I have a point that may have been a little bit of an outlier or somehow is misbehaved. And the bottom right charts, the Cook's distance and perhaps the difference in fits so the difference in fits tells me if I include or exclude that data point, how much does my model change, or does it still fit the data? And here that data point is right there between the blue lines. So I'm going to say even if that data point is a little bit of an outlier, it's not doing any damage. So I'm going to move along, and I can look at the model graphics here. Maybe look at the 3D surface just for fun. And you can see a lot of things going on. If I change the catalyst amount, you can see that behavior, that system becomes really, really, really different. Okay, so there's a lot of moving parts going on here, a lot of things that you can see. Well, let's also take a look at activity. And we'll start that analysis. And this one's more simple. This says a linear fit would be okay. So, all right, we go to the model, and it's going to say I have three linear effects to look at. I look at the ANOVA. I have a significant model, and I have a not significant lack of fit. That's good. And my fit statistics are all good. But one thing that I would observe here, and this can be interesting sometimes, I have a factor, like temperature, that arguably isn't bringing any helpfulness to the predictions that we're making. The p-value is very high. It doesn't seem to be statistically significant. So, for example, just think about it for a minute. Let's imagine I'm trying to find the factors that help me predict the weather in Kansas. And let's say I include something like phase of the moon. Well, phase of the moon doesn't actually have any bearing on predicting the weather in Kansas, I would imagine. But if I include it as a predictor, it's actually going to harm my predictive capability, right? It's a factor that didn't matter, but I included it anyway. And now I'm adjusting my forecast based on phase of the moon when in fact it didn't matter. Well, in this case, it would seem that the temperature is not statistically significant. So I might try to take that out. I might do what's called model reduction. Let's get rid of it and see if it does any damage to the predictive model. How would I know if it did any damage? Well, I typically look at this thing over on the right called predicted R squared, right? It's at 9276. Well, if I want my model to make good predictions, I want a high predicted R squared. I mean, that's not bad. That's probably just fine. But let's see what happens if I get rid of temperature. So I go back to the model, double click on temperature. It takes it out of the model. The M's are the terms that are in the model. Come back to my ANOVA. Okay, that all still looks good. And okay, I slightly improved the predicted R squared. So keeping B in, keeping temperature in, probably wouldn't have done any damage in this particular case. But the point is, I got rid of a useless predictor, and I certainly didn't damage the model, right? So model reduction was a good thing to do. The simplest model that predicts the information, predicts the data, is often your best. Now we can take a look at the diagnostics, and that all looks good. Well, now we're down to trying to figure out what the ideal conditions would be to achieve both the conversion and the activity. So now we're going to come down to numeric optimization. So a new tool here. I will click on conversion, and I want to do what with that? Well, I want to maximize it. And I don't want to accept any answer less than 80% conversion. And if I can get to 100, I'd certainly want to do that. So that's the little ramp here is showing you what your target is. It wants to chase up to 100%. That's going to be the best, but it won't give you any solution that's below the minimum here, below the 80. Activity, well, we want to target a particular value here. We like the value of 63, but it's got to be at least 60 and no higher than 66. So the little ramp down here at the bottom is telling you, that it's got to be between 60 and 66, but if you can get close to 63, it would be happiest. Well, we look at solutions, and there it is. So by balancing those two goals that we have, we can see that the ideal condition will be, well, we have a time at 47, the temperature at 90, the catalyst at, 2.7. And there it is. We can pretty well nail the 63 on the activity goal, and the conversion will be about 91%. Okay, so we've optimized within the design space for the two properties of interest. So response surface designs are useful when curvature or nonlinearity is anticipated within the design space, within the cube, right? We think that there's a more complicated behavior than just simply linear or two-factor interactions. The model terms will include quadratic or even higher order terms in addition to the main effects and interaction terms. The downside is that this will require more runs than the factorial designs, right? So that's why we don't start out right here, is because, okay, we want to make sure with the screening designs and the characterization designs that we've whittled down our list to the minimum factors that we can before we do the expensive DOE, before we do the one where we can optimize, right? The more factors you include, the bigger these things are going to get. So we only want to work with ones we know are important. And the numerical and graphical optimization tools that we just saw will find the optimal conditions to satisfy, one or more criteria. Now, if you find that this type of work, if these types of things are of interest and something you want to explore more fully, well, we do have opportunities to attend courses, distance learning courses, through Zoom, or even in person for a particular company if there's 6 or more people involved. And modern DOE for process optimization will cover basically the kinds of designs we talked about, the factorial and the response surface designs. I believe there are some upcoming courses in February, in March, that might be of interest for anyone who wants to broaden your skills a bit more completely. You can learn more on our website or contact workshops@states.com. Now we're going to go one step further, and we're going to look at mixture designs, or actually we're going to go all the way down to the bottom one, a combination mixture plus a process factor, and we're going to see what happens there. Well, first of all, what makes a mixture design a little bit unique is that, well, the factors that we're studying are, well, guess what? They're ingredients of a mixture or a formulation. And the response is driven by the proportion of the ingredients, not the absolute amounts. So that causes a little bit of an issue that we have to resolve. If we did the factorial design in a mixture case, let's say we're making lemonade from lemons and water, well, we would look at, we'd look at 1 to 1 here, right? We'd look at, 2 to 1 here. We'd look at 1 to 2 here, and we'd look at 2 to 2. But the problem that we have is that these two are what? They're the same formulation. I just have more lemonade made. So I really didn't do like I would in a factorial design. I really didn't look at the high and the low, and because all I did was run the same formulation twice. So that is a little bit of a problem that we have to resolve by bringing a constraint into the story. And if I have 3 factors, well, it's the same thing, or 3 components. Instead, I'm not free to choose independently all 3 of them, because like with a mixture, if I know 2 of them, well, the third can be calculated by difference, can it? Right? I mean, if they sum to 100% and the first 2 sum up to 50, well, the last one's going to be 50%, right? It's calculate by difference. So we have to kind of work that into the overall story. And so the mixture designs are specifically set up to be able to handle those constraints. So a mixture amount experiment is where, well, it's like fertilizer. Okay, well, not only the impact of the fertilizer is not only impacted by the composition of the fertilizer, but also by how much you apply, right? Or if you have a headache after the webinar and you want to take an Excedrin, Well, it's not only impacted by the composition of the headache medicine, right? The amount of aspirin, acetaminophen, and what is it, caffeine, and an Excedrin tablet, but you also get to pick the dosage, 1 tablet or 2. Okay, so it's the composition plus the amount that's involved. So that's the kind of experiment we're gonna look at here. And here we're gonna make an ibuprofen coating. We're trying to make a timed release ibuprofen tablet. And here's what we're going to do. We have 31% of the formulation that we're going to change. The rest of the 69% is probably something like water or surfactants, but it's held constant. So we're going to work with just the 31%. And we have 3 materials that we're going to use in this coating that we're going to play with. EA will go from 7 to 20% that we'll explore. MMA 7 to 20, and this one 4 to 14, right? So we're going to play within those ranges, but we'll always sum to a 31%. And then the amount that we're going to apply to the tablets in this laboratory coater, we're going to use 15 to 25 mLs that we're going to explore. And in the end, what we're going to look at how much of the drug is dissolved after 1 hour and 12 hours, and we're going to hit some target values of interest. So that's the goal. So we want roughly 20% dissolved in 1 hour, and we want about 90% of it dissolved in 12 hours. So that's the objective. Okay, I wonder if we can do that. I bet we can. So let's get this one opened up. Let's see here. Is it this one? Yeah. So we're going to come all the way down here, even past mixture, because this one's going to be a custom design optimal experiment. We're going to use 3 mixture components and 1 numeric factor, the amount factor. So we'll hit next, and here's what it lays out. Remember, it sums to 31% total, the formulation. Each individual will go through these prescribed ranges, so it will create a design that works within that framework. The amount will be the mLs injected into the lab coater, and we said that's going to go from 15 to 25. This is the optimal design. So this is a custom computer created design for us. We're going to accept the defaults here, so this will be 28 runs. I have 2 responses of interest. We finish the design. And boom, there it is. Now I can round these. These are rather specific. I'm not going to go to the lab and measure 14.5783. So let's round the components to, let's say, 1 decimal place. That might make a little bit more sense. So that looks a little cleaner. Okay, so, and the mLs, you could probably do that too. But let's get our data and analyze it. We could simulate this, and this will be ibuprofen. And there it is. Well, we know what to do. This is our 3rd shot now, so we're going to come under Analyze and go to our 2 responses and give this a shot. So here is, we'll start the analysis. It's a little more complicated layout, but at the end of the day, we're going to do the same thing that we did in response surface, because mixture designs are actually, you know, the response surface designs, but they're just tailor fit to the mixture environment. So we'll go ahead and take the default. We'll click on this. Now, the one thing that I will say with these types of designs is that model reduction almost always applies. Remember how we took that B term out earlier? Well, we're gonna do model reduction, but there's a simple way to get it done. So we're going to use this auto select feature, maybe p-value backward. That's a longer story, but we'll just take the default here as p-value backward, and we'll let it get rid of some of the terms. We'll click on ANOVA, and it needs to add some of them back to support hierarchy. To make a long story short, the answer to that question is always yes. And then here becomes the simplified predictive model, right? It's significant, the lack of fit is not significant. Fit statistics are fantastic. We can look at the diagnostics. I'm happy enough with that. Well, let's do the 12-hour one now. We'll start that analysis. Okay, so it's again a quadratic bilinear, but in parallel, it's testing a subset of the terms that could be included in something called the KCV model. That's another longer conversation, but suffice it to say, it will pick the better of the two and recommend it, which in this case is what it did. It chose the KCV model. I will do the model reduction again. I'll accept it. And this time I don't have to fix hierarchy. I got lucky, but there it is. So I have a good fitting model. Check the diagnostics. It's all suitable. So we have two good models that we can use. So let's go ahead and use numeric optimization. And I have some goals here. So I want a certain amount dissolved in 1 hour. I'm going to target, what do we say? We want to target 20% dissolved in 1 hour. But I'm going to give it a little flexibility to go as low as 10 and as low as 30. Okay, so as long as it's in that range, I'll at least deem it, suitable for consideration. The 12-hour, we had a goal. We want to target, in this case, 90. And we're going to go from 80 to 100, right? So as long as it's in that range, we'll be okay. We click on solutions. And boom, there it is. So there's the formulation of interest and the coding quantity. And, there's the anticipated amount that would be dissolved in 1 hour, roughly 25% and 87% after 12 hours. So something along those lines. What we always recommend is going back and doing some confirmation runs. So over here on the left, there's a tab for confirmation. And what that would do, it would ask us to run, preferably multiple, let's say 3 test cases to prove that, the predictions are holding and that indeed is a proper recommended and successful zone to operate. So that would be what we would say should be the next step, is doing some confirmation runs. All right, so so mixtures have a built-in constraint, the formulation sums to a total. It's a response surface design, but because of the constrained total, special approaches are needed to build these DOEs. They use something called Cepheid polynomials to create the predictive models. We can create custom or optimal designs for, in all kinds of situations, so that if there's not a canned algorithm, a central composite, or some other standard design that is suitable, we have a very good way of creating a very useful design using the optimal design features. If you work in the world of mixtures or formulation development, or can tweak between the formulation and the process factors, like we did in the ibuprofen case, you might be interested in a mixture design for optimal formulations course to improve your skills. And again, if you have 6 or more at a given company, we could come out and instruct personally. But if you're interested in that environment, you might want to take a look at our website for what the available options there. I think there's a course, I believe it's February for mixture, I think. Could be wrong, but it's out there on the website. And then if you are interested, you can contact workshops@states.com for additional information. So in summary, a DOE is a planned multi-factor approach to efficiently and effectively determine cause and effect relationships. The statistics provide powerful and and make your conclusions credible. Design-Expert specializes in DOE, and we have a wide variety of design types that you can choose from. We do have some books written by States folks that are, they're not the big, thick, heavy textbooks. These are more practitioner level understanding of the concepts that we should understand to conduct DOEs. Those are available. You can kind of see where. You can look at our website for success stories in industry. you can look at YouTube. There's a lot on YouTube. If you look up trainings and different webinars, they're out there. White papers, again, on the website. If you do have questions, feel free to send them to stathelp@staties.com. We will follow up with you usually quite quickly. And that's really the story. I do have one question out there. Let's see. Can I use superior terms that are not alias to improve fit to the model? So point number one, never use an alias term. You're correct about that. And we have had various answers to the question that you're asking. And I would say the most confident approach is not to include those higher order terms, although we have had success stories where those have brought value. So you're kind of on a gray zone on that particular topic. You can try it, and if it seems to give you helpful information, as long as it's not aliased, you could try it. Although the statisticians amongst us kind of suggest doing otherwise. I would like to see a little bit more complete answer to that question myself. And yeah, for okay, what type of distribution should I start considering that are not okay in my data inverted once shape, but I don't know if it's okay. All right, so that particular question might be a little bit more involved, and I would invite you and encourage you to maybe write that up and ask stathelp@staties.com. That one is a little bit more broad and might become a little bit more specific to what you're looking at, and perhaps if you're willing or interested to share your data set, then we could take a look at it and help you understand it. At first brush, what I'm thinking is your data might be better analyzed by using a data transformation. So data transformation, for those that aren't aware, are when we do a mathematical operation to our data before we analyze it. For example, in the world of polymers, there's a natural relationship between the molecular weight of a polymer and its resulting viscosity, but it's not a linear relationship, it's exponential. And so taking the log of the molecular weight before analyzing the data is going to be a more natural way to go about it, and it's going to analyze more cleanly. So you may have something like that to think about. When is a box banking useful? A box banking is useful as an alternative to the central composite design when you're going to take those axial points and bring them into the face. Okay, so for example, the axial points want to be outside the cube, but if I'm running catalysts, say at 1 part per million to 3 parts per million, and if I move those points outside the cube, maybe it wants me to run catalyst at -1 part per million. Well, I can't do that. So I need to move those axial points into the faces of the cube to make it practical. And when I do that, you might find that a box banking will give you a more efficient design when you're only going to work with 3 levels of factors. So that might be a long-winded answer to your question, but number one, it's going to be a 3-level design, right? So I'm not going to put those axial points outside the face of the cube. And it tends to be a little bit more efficient, a couple of less runs than the central composite would be. It's a good design. So I mean, if I'm going to do 3 levels of a design, I'm often going to be thinking about the box banking. Okay, I think there are no more questions that I'm able to answer. Again, if there are, please send them to stathelp@staties.com. I thank you for your attention. We've gone a couple of minutes past, so I thank you for your hanging in there with me, and I wish you the best of success. Thank you.